Okay, guys, this is Independent Samples T-Test video for my math6610. Let's take a motivating problem here. I promised you in math6610 that what we would do is present things from a non-theoretical perspective. And trust me, the theory on Independent Samples T-Test isn't that difficult, but staying in line with my promise, let's take an example here. Okay, so let's say that there's a hypothetically, and by the way, I made these numbers up. I randomly created some stuff, and so don't draw any real life conclusions from this illustration. This is just manipulated data so I can run through an illustration. Okay, so let's say that there's a high school administrator at a very large school district that suspects there may be a difference in SAT scores across gender. So what he or she did is, it looks like they took a random sample of students, and it looks like they took SAT scores from 54 females and from 46 males. Okay, so again, they want to test if there's a difference in average SAT across gender. Now, let me go back to the blackboard here and just talk a little bit. First thing I want you to get in a habit of doing, and guys, keep in mind here, granted I'm teaching Independent Samples T-Test now, but I know where we're going, where we're headed, so I'm really setting the foundation for bigger, better things. I don't know about better, but it's just more complicated statistical techniques than an Independent Samples T-Test, which is just about as easy as it gets. So anyway, the first thing we want to do is we want to get in a habit of using Excel to cleanse data. Now, that's just driving me crazy out here. So use Excel to cleanse our data. Guys, you can actually import the data into R and cleanse your data there, but I have found it much easier to work with Excel because of the copy and pasting option, and then bring the data into R as a .csv file. But what I want you to think about in cleansing data, I always want you to get your data in the form where the vertical represents the variables and left to right represents the cases. Studies have shown that when someone with no prior statistical training or statistics education looks at a data set, they will typically read from left to right. Left to right's where all the juicy gossip is about people. So for example, you could come down to subject number 22 and you could find information about that particular person. Well guys, people who have statistics background could care less about horizontally. We are interested in the variables, describing the variables and making conclusions from the variables. So someone with statistics background looks at a data set. We're more interested in the quantitative variables. What's the mean, what's the median, what can we infer? The categorical variables, what percentage of, in this example, are males and what percentage are females. So just keep that in mind, not only when you set up your data set, that we have to have the variables on the vertical, and we have to have the subjects or cases on the horizontal. Okay, and I'll show you how to do that in just a second. The second thing I want you to get in a habit of doing is exploring your data. And when I say your data, as I say at the bottom of the page, this is just what's going on with our sample. I think we have about 100 students from the school district. Let's just describe important characteristics for those 100 people before we get into the fancy stuff and start making inferences to the larger population. Yeah, things we want to do there. We want to be able to report and interpret appropriate graphs, and obviously we want to look at some basic descriptive statistics. We can't draw much from that, but we still want to take a look at it. Second thing we want to do is we want to conduct inference. In this case, we would run what's called an independent samples t-test. The assumptions for the independent samples t-test are we need normality and we need independence. Independence is the biggie here. The next video I'm going to show you a dependent samples t-test. But the independent samples t-test means that the measurements from the two samples don't appear to be related. Yeah, typically a random sample, if you truly conduct random sampling, your independence assumption will be taken care of. Number 3, continued. We get into a situation, let me write that where someone can read it. Gosh. We get into a situation where what technique are we going to conduct? Are we going to do a pooled t-test or an unpooled t-test? And guys, that has everything in the world to do with whether or not the variances of the populations that we're drawing our samples from, whether or not they are equal. Now this gets really, really tricky, and I'll explain it as I go through the illustration. Guys, the fourth thing is compute the test statistic p-value in the 95% confidence interval. This is clearly the inference part, because this all leads to rejecting or failing to reject the null. The fifth thing I want you to get in a habit of doing is, we talked about effect size and power. Guys, I encouraged you to download gpower in the previous, or one of the previous videos. Hopefully you've done that. If you haven't done that, I strongly encourage you to pause this video and download that. Sixth thing, conclusion. I want to teach you not only to appropriately conduct these statistical techniques, but exactly how do we report the results. So this will be in the summary statement. All right. So the first thing, let's get off the chalkboard and let's get back to our data set, and let's cleanse the data. Now when I see this here, first of all, I look from left to right. Is that a case? No. That's information on one female student. That's information on a male student. So guys, we don't have our data set up correctly. We don't have a data set here. We've just got some numbers, and we've got them in the columns across males and females. What we need to do is we need to have a subject number, and I'm going to fill that in a second, but 1, 2, and so on. Another variable in this is SAT, and another variable is gender. So I'm going to do some creative copying and pasting here. So I'm going to go down and copy all the females first. Now this is really the reason I prefer to use Excel, because this kind of stuff is just really easy. Now I'm going to go ahead and put in F's here for female, and what I can do is just highlight the F and then just kind of drag it down, and it's just really going to conveniently put in F's all the way down to the last female SAT score. Alright, next thing I want to do is I want to go over and get the male scores. Copy those, and I want to paste those below. So guys, these are all going to get M's for obvious reasons. Alright, cool. Now subject number, if that's something that you want, and sometimes you do, what I may do here is go equal to that cell plus 1, and this is going to allow me to do the whole fill down thing. So I can come down all the way to the end of my data, into my measurements. Pretty sure there were 100, but I'm not sure. Can we find out, right? Yeah, so I have 100 participants in this study. Now, I don't want this, I want to import this into R, but I don't want R to have those columns because that'll just confuse things, so I'm going to delete those. So guys, notice now that I've got my data set in proper form. On the verticals, I've got the variables, subject number, SAT, and gender. And on the horizontals, I've got information for the cases. So for example, this 15th person has an SAT of 558, and this person's a female. Now, what I want to do now is I want to go up here and save this. And I want to do a save as. And I'm going to call this SAT. Now, you can get into stuff here. You can do SAT across gender, whatever it may be. I like to keep this small because when I go into R, I've got to worry about capitalization and spaces and everything. So if I keep it simple, it just seems to make things easier. Okay? So I'm going to save it. Well, something already exists for that. So I'm just going to call it SAT gender. That's something I should be able to easily remember when I get to R. So it's going to tell me all this stuff. It acts like I'm committing some crime, but it's all good. All right, gang. Next thing I want to do is I want to get my data into R. So I've got to set my working directory. And then I need to get my data. Now we should be old pros at that by now, so we'll see their data set. That's just something kind of interesting. It automatically assigns subject number in the left, so that's kind of irrelevant. Subject is just is arbitrary anyway, so it's not something we're ever going to include in our analysis. But I guess okay. Well, let's go for it. So, guys, that's complete step number 1 in terms of cleansing the data. So, step number 2. Let's take a look at some descriptives. So, first thing I'd want to do is take a histogram of SAT. Okay, what's going on here? All. Okay, so we got to attach our data and then go histogram. So this is there's no reason for us not to think that these measurements came from a normal distribution. Clearly the sample scores are bell-shaped and symmetric, and to me look very, very supportive of coming from a normal distribution. The next thing I'd want to do is look at box plots, and I'd like to look first of all at all the SATs, and we've got one outlier. It's not that much above the highest non-outlier, and again we got the symmetric looking distribution. Probably most importantly, I would like to look at, how did we do gender here? Is it capital G? Or, yeah. I'd like to look at box plot across gender. So what am I looking for there? Well, I'm looking for center, spread, and outliers. So center, spread, and outliers. So the dark lines there are the medians, so I compare the centers. And it looks like the median male score is slightly above the median female score. Now I look at my spread measures, and in this situation we look at quartiles. I see that the Q3 for male is higher than the Q3 for female. I see that the Q1 for male is higher than the Q1 for female. And overall, I don't see a lot of difference in the variances or in the spread of the overall scores. Relative to the outliers, I can't help but notice that the top 2 scores here for males are outliers within their own distribution within gender. They weren't when we piled them all together, female and male. And there's 2 low scores that emerged as outliers. So again, I'm just making statements about these 100 participants when we divide their scores across gender. I'm not making any inferences whatsoever. The only statements I can say is, well, for these 100 students that are in my sample, these characteristics have emerged from taking a look at the pictures. Now, the next thing I'd want to do is I'd want to get into to some measurements, and I'd like to know the mean across gender. So, guys, I can use what's called t-apply, and I'd like to do SAT across gender, and I'd like to report the mean. So, guys, what this is going to do is this is going to report the means across gender for these 100 participants. Now, I saw earlier that the sample size, but I want to go ahead and show you how to. Unlike you would think that there would be N or sample size or something. It's not. In our length is the sample size. So what I can say here is for these 54 participants who were female, their average SAT was 514.5. And for these 46 male participants in this study, their SAT average was 563.02. Now, can we say that the males for this school district, all males, is higher than for females? Not yet. All we can say right now is that the male mean SAT for these 46 males is higher than the mean SAT for the 54 females that are included. I'd also like to get into standard deviation. So again, center, spread, outliers, okay? And the standard deviations appear to be pretty close, okay? Now, moving into the third step, should we conduct a pooled or unpooled? Guys, this is the tricky part, okay? Let me go back to the blackboard. And I got kicked off for some reason. Alright, it should be coming. Okay, first of all, to pool or not pool. My hand keeps hitting and it drives me crazy. Okay, first of all, the only way that we should ever pool is if there is evidence to support that the variance for female SATs is equal to the variance for male SATs. Now, in general, the variance of population 1 is equal to variance of population 2. A couple of ways we can test this. Number one, extremely informal. What we can do here is we can take the smallest standard deviation, take 2 times the smallest standard deviation, and if the highest standard deviation falls in this interval, then we can assume that we have equal variances. Now, having said that, I don't like this approach, but it's something that you see in textbooks from time to time. So I think our smallest standard deviation was 113 or something. Let me go back and get that. 113. So if I double 113, I get 226. So I get the interval 113 to 226. 117 is clearly in there. So this very, very, very informal approach on assessing whether or not equal variances are met actually gives us evidence that it is satisfied. The second way, and much more acceptable, is called Levines Test of equal variances. Now let me tell you a little bit about Levine's test of equal variances. First of all, the null hypothesis. Is we have equal variances. The alternative hypothesis is, of course, that the variances are not equal. 0.05 again is typically the threshold that we test at. So if we get a p-value less than 0.05, we would assume that we do not have equal variances at p-value higher than, well, 0.05 or higher. We do not have statistical significance. We assume equal variances. Now, I'm going to show you how to run this on R, and it takes a little bit extra. Now, there's something called Levine's test for equal variances, and let me show you how it works. Well, I'm going to show you how it doesn't work actually. If I go Levine test of equal variances, the first thing we do is we put in our quantitative measure, which would be SAT. And the next thing we put in is our gender. And the next thing we put in is our center. Well, we're doing variances, so we would want the center to be mean. Now, when I run that, it can't find the function Levine's test. Now, the reason is it's not included in the version of R that I downloaded. So what we have to do, we have to install a package. And guys, this is going to happen a lot throughout the videos coming up. So to run Levine's test of equal variances, we must always load the package cars. So guys, we're going to go install packages. Guys, when we install packages, we have to include, we have to put the name of the package we're installing in quotations. Now, the next thing it's going to ask us is to select a crayon mirror. I really don't have anything to back this other than it just works. But I always go to USA CA1 and click OK. Now, depending on the speed of your computer, there's going to be a slight delay. It's going to go through some installation stuff. And it says car. Oh, shoot, I messed up, guys. First mistake I've ever made. Yeah, right. It's not cars. It's car. My bad. Alright, so once you get it correct, it installs the package. And now what we need to do is we need to install the library. But when you do the library, you don't include car in quotations. So all is good now. So guys, what we can do now is we can run Levine. Let's see, Levine test And run SAT, gender, center equal the mean. Yeah, I didn't think that was right. I think it's this actually. Levines Test. Should have written this down, but I didn't. Alright, that's it. So the Levine, the T has to be capitalized. It's funny communicating with a, or competing too, communicating with the machine, how these things can happen. Well guys, in running the Levines test for homogeneity of equal variances, we can see that we have an extremely large p-value, almost equal to 1, which is really strong evidence. We shouldn't reject. We do not have statistical significance. So our conclusion, we fail to reject. So our test is not statistically significant, so we assume equal variances. Now, guys, caution. Let me put in caps here so I can get your attention. Let's go back and let's just think about the logic of a test of hypothesis and what we really know after conducting a test of hypothesis. Do we now know that that we have equal variances? Absolutely not. All we can say for sure at this stage of the game, I wish this thing wouldn't kick out, but it's going to, and there's nothing I can do about it. So what do we know? Well, there's not enough evidence to reject that, so our evidence is in support of the null hypothesis. But guys, that doesn't mean this is true. That just means there's not enough evidence from our sample data to reject that claim. So where does that bring us? That brings us to an important decision. Important topic. When can we assume equal variances? I'm not going to let you get away with the smallest standard deviation multiplied by 2, create the interval. I'm not going to let you get away with that one. I want you to learn Levine's test of equal variances, obviously, because I just pointed it out to you. But at the end of the day, we can assume equal variances when there is a theoretical support. When the equal variances are supported by theory. Now guys, if we go to the SAT website and look at the information provided by those folks, they will tell you that based on their analysis that the variances for males and females are equal. So guys, this is the only time that I would ever really permit you to use a pooled t-test, independent samples t-test, is when there is theoretical support. There's evidence beyond creating an interval from the small standard deviation and multiply by 2, and even from Levine's test of equal variances. Now later on this semester, or later on in the course, we're going to rely on Levine's test a lot more. But in this situation, in the independent samples t-test, I want you to have theoretical support before you run a pooled t-test. So let me tell you briefly the difference. The pooled t-test. First of all, assumes equal variances. Has the degrees of freedom that are very easy to and it creates what's called a pooled variance. So it combines the variance, comes up with one pooled variance, and uses this as an estimate of the standard error for the distribution of the differences in population means, actually in sample means. The unpooled doesn't assume equal variances. In my opinion, this is preferred. The degrees of freedom are quite ugly. The calculations are quite insane here. And the standard error, the estimate of the standard error, is really an easy calculation. It just takes the variance of the first sample divided by the sample size plus the variance of the second sample divided by the sample size, and takes the square root. Now, just in case you care, the degrees of freedom for this nasty mess, let's see if I can even remember this. That should be an EM guess. I think this is right. Yeah, pretty sure it is. Let's see, well, let me check to make sure I'm not giving you something crazy. No, I didn't write it down, so guys, I'm pretty sure that's right. So guys, at the end of the day, remember that the calculation of our test statistic takes a look at the difference of the sample means minus our claim in the population divided by the estimate of the standard error. Now, because our null hypothesis is we assume that mu1 is equal to mu2, which is equivalent to saying that mu1 minus mu2 is equal to 0, we can come in, assume that part's 0, giving the test statistic to be this. All right, gang, let's make it happen. So because I can visit the website and assume that the variances for male SATs and female SATs are equal, I'm going to carry out a independent samples t-test, and I'm going to do a pool t-test. Now, one more thing. When we have an unpooled, this is also known as a Welch t-test, and the pooled, well, the pooled is not. So this would, if we have a pooled, it's not a Welch's t-test. And that's going to be something that will show up here in just a second, I believe. All right, gang, let's go for it. Let's go to R and carry it out. See what we get. Come on, computer, don't leave me now. Okay, so the way I'd want you to carry out the t-test would be to go t-test, and we want our SAT cross gender. Now, once we get this, there's a couple of things that we need to put in. First thing, we want to tell R that we don't want a paired t-test. We'll do that in the next video. So we'll include paired equal false, and also variances equal we want to be true. Now, another thing that we could put in, if we have an alternative where it's greater than or less than, as I showed you in a previous video, we would just type out alternative. I don't want that. Equal, greater, or less than. We want the default here, which is a alternative not equal to. All right, gang, when I run this, I'm going to get some results. Our test statistic is negative 2.09, telling me that our sample mean difference is 2.09 standard errors below the claim in the null hypothesis, which the mean difference is equal to 0. Notice we get the nice degrees of freedom, 100 minus 2. And notice we get a p-value of 0.039, which is statistically significant, indicating that there's evidence against the null, indicating that there appears to be a difference, a statistically significant difference in mean SATs across gender for all students at this large school district. The 95% confidence interval runs from negative 94.51 to negative 2.53. This tells us that 0.95 probability, the mean difference between ACT for male and female appears to be somewhere between 2.5 and 94.5. Down here we get the descriptive statistics, which obviously we already have. Now, notice this just ran a two-sample t-test. Let me show you what would have happened if we hadn't run variance equal true. So if I just did the default where we have SAT across gender, and I put still paired equal false, but I don't put the variance equal variance dot equally true, it will go to the default of false, and it's going to run what's called a Welch's two-sample t-test. And guys, this is the equivalent of an unpooled t-test. You can see that your test statistic is a little different. The reason is your degrees of freedom are different. Therefore, the estimate of the standard error was a different value. So you're still in the numerator. You still have the same sample mean difference, but the estimate for the standard error is different based on the degrees of freedom and the calculation of standard error. So actually the difference in the degrees of freedom leads to the difference in the p-value. Up here we pooled the standard deviations to get a pooled variance. So we kind of combined them because we assumed them to be equal. Down here we had a different calculation. You can see that the 95% confidence interval isn't a lot different. And in both cases, again, we get a statistically significant result. So boys and girls, at the end of the day, this is one of the very rare cases that you will be able to run a pooled sample, independent samples t-test. So enjoy. Usually you're not going to be able to do that. Guys, next thing we get into is this step we calculated the test statistic, which would be negative 2.09. We calculated the p-value, which was 0.039, less than 0.05, and we calculated the 95% confidence interval. Guys, the next thing is to calculate the effect size. And let me go back over and show you how we calculate the effect size here, and try to clear up what's sometimes confusing for students. All right, effect size for now, guys, remember, up to now, effect size, again, takes the sample size out of the equation. It gives us a standardized measure, which can be used to compare effect sizes from different studies. And right now, we've looked at Cohen's R or D. Remember, for R, it goes from 0.1 to 0.3 to 0.5. Small effect, moderate effect, large effect. And on D, it goes from 0.3 to actually 0.2 to 0.5 to 0.8, small, moderate, large. Well, guys, the effect size is probably easiest to calculate for independent samples t-test, is the R, and the R is, if I can remember this, so it's going to be t squared, and again, t is your test statistic, divided by t squared plus your degrees of freedom. Take the square root and get the value. So let's go do that. Maybe. All right, so effect size is going to be found by taking the square root of t squared. Let's see, it was negative 2.09, so we know that squared divided by the quantity 2.09 squared plus the degrees of freedom are 98. So our effect size is 0.21, which according to the criteria that we set back here, it tells us we have somewhere between a small to moderate effect. Okay, next thing we'd want to do is we'd want to get some power analysis. And what I want you to do here is become consistent and rely on G power. Huh. So let's bring up G power. And what I want to do here is go over to the test family. Clearly we have a test statistics T. I want to go down to mean difference between two independent means. We have a two-tailed test because we did not equal 2. Our effect size was 0.21. Our error 0.05. Oh, wait a minute, guys. I'm totally losing my mind here. We need to go to achieved power. We want to do a post hoc here. So we have a two-tail. Our effect size is 0.21. We had a 0.05. Our sample size in group number 1 was, oh shoot, I forget, 54. Daggone it. So 54 and 46. I didn't trust it. So 54 and 46. So we can run our power. And it looks like we have power of 18%. Guys, that's pathetic. Power of 18%. You really, well, we detected a difference, but that's way too low power. Guys, you typically want your power somewhere at least 0.60. I'm thinking typically more around 0.80. So let's get out of this, and the final step would be to report the results. So I would say something to the effect, first thing I would do is make a statement about the sample. So I would say on average, male SAT scores. Okay, let me go get the descriptives. All right, so the male SAT was 563.02. The female was 514.50. Standard deviation for males 117.92, and for females 113.41. Sample size was 46 males and 54 females. So let's go back. Alright, so I would write the mean for males 563.02. Standard deviation 117.92. So on average, male SAT scores are greater than female SAT scores. Then I would say this difference is statistically significant. Alright, gonna have to go back to Alright, so negative 2.09.039. So let me write some of this stuff down. This was this summer. This was the stuff that really gave my students the most problem. Was well, I mean, some of the methods that we learn are you know, more complex and much more complex than this. So there was some other things, but mostly, once they found something, how did they write it up? So that's why I'm taking a lot more pain in trying to do this and be consistent through all the videos. All right, so T of 98, guys, your degrees of freedom will always go in this spot. Your p-value is less than 0.05, but not less than 0.01. And then I would say, however, it did represent a small to medium effect. Given a very low, or given very low power. And I forget, what was our power? 17%. Uh, 17.9%. All right, guys. So that's the way that we could write that up in kind of one sentence. Go back here. So, well, you've got that's the great thing about it. You've got the power of pausing and things of that nature. So guys, that's a very thorough illustration of an independent samples t-test. So that's all I got for you. Take care.